around us is made up of carbon compounds. Life is based firmly on this remarkable element. The useful property of carbon is an electron arrangement, allowing 4 bonds to form with other atoms. It can also bond with itself. These simple properties can lead to half the known compounds being compounds centered around carbon. The study of carbon compounds and their properties is called organic chemistry. Carbon compounds easily fall into families or series. The simplest class of organic compounds are the hydrocarbons, containing the elements hydrogen and carbon. This is divided into aliphatic and aromatic hydrocarbons. Aromatic hydrocarbons are ring compounds containing the benzene ring, which has a unique bonding structure. Aliphatic hydrocarbons are usually chain compounds that do not contain the benzene ring. They fall into 3 groups: alkanes with single bonds, alkenes with double bonds, and alkynes with triple bonds. To understand the naming of carbon compounds, we can use the alkanes, in which all the carbon atoms are singly bonded to one another. Methane is a single carbon atom combined with 4 hydrogen atoms. Ethane has an extra carbon with the unused bonds occupied by hydrogen. Propane has 3. Butane has 4 carbons. Pentane 5. Hexane 6. Heptane 7. Octane 8. Nonane 9. And decane. After that, we usually just give the number. For example, C25. So this table shows us the basis of naming hydrocarbons. The carbon atoms don't need to string together in a long chain, as in our molecules so far. The chains can branch in many different ways. For example, we can have straight butane, which is C4H10. However, in methylpropane, we see the formula is still C4H10, but the structure is very different. These 2 compounds are quite distinct and have different melting and boiling points and reactivity. The name methyl comes from the fact that the side chain is actually methane, CH4, with hydrogen removed. 2 or more compounds with the same molecular formula and different structures are called isomers. Another good example of isomers are pentane and methylbutane. We'll look at more complicated branching later. Most of the hydrocarbons we use occur naturally. We get them from crude oil or natural gas. Oil refining separates the hydrocarbons, and petrochemical processing converts them to a variety of products, which are the basis of modern manufacturing. The properties of these compounds vary gradually. The simple ones, C1 to C4, are gases at room temperature. The intermediate ones, C5 to C15, are liquids, while C16 and up are usually solid. How and what we use them for depends on their boiling points, and for the simple ones, how easily they can be liquefied. Methane is found as natural gas and must be refrigerated before it can be compressed and liquefied. Ethane is the same, but it does not have to be compressed and cooled quite as much. It is one of the main components of natural gas. Propane, with 3 carbons, we use as portable bottled gas and is commonly called LPG. It can be liquefied at room temperature, but needs a fairly strong pressure vessel. Butane needs less pressure to liquefy it and can be carried in lightweight disposable containers. At low temperatures, butane will not evaporate, so this is a problem in the snow. Propane will work in the cold, but the container is heavy to carry. Pentane is sold as lighter fluid and is liquid at room temperature. Hexane is similar and is used in some processes as a solvent. It is in adhesives because it readily evaporates. C6 to C12 make up gasoline. The higher ones would be highly branched. C12 to C16 are kerosene and jet fuel. It has the advantage that it is not as volatile as gasoline, and therefore will not catch fire so easily. Dieseline is C15 to C18. Lubricating oils are C16 to C30. The wax in candles is actually C28 to C30. And the paving for the roads is C30 and up. Carbon is able to form a double bond between 2 carbons. This is ethene. Using our naming table, the eth is used to show 2 carbons. The ene indicates a double bond. So all the alkenes have at least 1 double bond between carbon atoms. Carbon also forms a triple bond. This is ethyne. The ine indicates a triple bond. So we can get propene and propyne. For butene and butyne, there are 2 places where the double or triple bond can be. This is 1 butene and 2 butene. 1 butyne and 2 butyne. The number is essential in naming these compounds, as it describes where the double or triple bond is. As we add more carbons, we get 1 pentene and 1 pentyne. One hexene and 1 hexyne, 1 heptene and 1 heptyne, and so on. As the chain becomes longer, there are a greater number of variations for the positions of the double and triple bonds. Also, branching is possible. If there is more than 1 double bond, the name changes slightly. This is 1,3-butadiene. The basic naming procedure we have used also helps name another group of carbon compounds, the hydrocarbon derivatives. These are molecules that are basically hydrocarbons that have additional atoms or groups of atoms called functional groups. Each group has its own characteristic chemical properties. The first group we look at is alkanols, also known as alcohols. If there is an OH bonded onto a carbon, the carbon compound is an alkanol, and we use the ending "-ol" to denote this. So with one carbon, it is methanol. 2, ethanol. 3 carbons, propanol, and 4 carbons, butanol. Once again, there are isomers. There is 1 propanol and 2 propanol. Or 1 butanol, which we saw before, and 2 butanol. There is actually no 3 butanol, because it is just 2 butanol looked at from the other end of the chain. In the naming of all compounds, we number from the end which produces the smallest numbers. To form an alkanol, OH groups can be added anywhere along the chain. If more than one OH group is added, the substance becomes a polyhydric alkanol. Ethanol has only one OH group, and so is not polyhydric, but we are familiar with it because it is the alcohol in alcoholic drinks. The first polyhydric alkanol is 1,2-ethanediol, commonly known as ethylene glycol, and is used as an antifreeze in car coolant systems. The next is 1,2,3-propane-triol, or glycerol. We know this commonly as glycerin. As we see, the polyhydric alkanols are named with the suffix diol, triol, and so on. If an oxygen is double bonded to a carbon atom on the end of a chain, the compound is an alkanal. We use the ending "al" to denote alkanals. These are also known as aldehydes. Methanol is commonly called formaldehyde and used for preserving biological specimens. Alkanols typically have strong odors. So we have methanol, ethanol, propanol, butanol, and so on, up to decanol. Then the number of carbons takes over the naming again. There are no isomers because the oxygen must be on the end of the molecule. If a carbon is double bonded to oxygen at a non-terminal carbon, the compound is an alkanone. We use the ending "-one" for this. They are also known as ketones. They start at propanone. There is no methanone or ethanone because you always need at least 3 carbons. Then butanone, pentanone, and so on. From pentanone on, the oxygen can be on different atoms, so the name changes, like 2-pentanone and 3-pentanone. There is no need for a number on the first 2, as there is only one choice of carbon, the C2. Alkanones also have solvent properties. Propanone, commonly known as acetone, is used as a cleaner and solvent in the production of rayon. If the end of the chain is COOH, the chain is an alkanoic acid and has the suffix -oic. These are also called carboxylic acids. These follow the naming convention. So we have methanoic acid, ethanoic acid, propanoic acid, and butanoic acid, up to decanoic acid, and so on. Ethanoic acid is commonly known as acetic acid, which is in vinegar, and is used as a food preservative. Now we're going to look at the group of hydrocarbons called the aromatics. This branch of organic chemistry is based on the benzene ring. The structure of the benzene ring has intrigued and baffled chemists for many years. At first it was thought that in benzene there were 3 double and 3 single bonds, but now it is known that the 6 electrons of the 3 double bonds are shared equally by all the carbon-to-carbon bonds. The 6 carbon-to-carbon bonds are identical. They are intermediate between single and double bonds. Chemists often represent the benzene ring like this, where the circle inside the hexagon indicates the special type of bond. A benzene ring can have elements or groups of elements replacing one or more of the hydrogen atoms. Adding the OH group makes phenol, which is used in the plastics industry. Adding an acid COOH makes benzoic acid, used in food preservatives and artificial flavors. Adding a methyl group makes methylbenzene, commonly known as toluene. This is used in the petroleum industry and in making explosives. To name groups or elements added to the benzene ring, it is numbered similarly to a chain. With 3 methyls we have 1, 3, 5 trimethylbenzene. We could produce a compound 2,5-dibromo 1,3-difluorobenzene. If we add things to a benzene ring, the carbons are numbered to produce the lowest numbers in the naming, and the name is in alphabetical order. Rings can form side by side to produce naphthalene, which is the main ingredient of mothballs. Or 3 rings form anthracene, used as a dye. Just as benzene has a ring structure, alkanes and alkenes can join in rings of 3, 4, 5, 6, and so on. But the difference is they have normal single and double bonds. These have the prefix cyclo to indicate the ring structure. So for the alkanes, there is cyclopropane, cyclobutane, cyclopentane, cyclohexane, and so on. They are often represented by their geometric structures. For the alkenes, cyclopropene and cyclobutene do not exist. There is, however, cyclopentene, cyclohexene, and so on. They are also shown with their simplified forms.